Hi everybody. I just wanted to finish section 11.1 here. So in the first part we covered independent samples, and in the second part here we'll cover dependent samples, and then we'll also talk about how to calculate the sample size. So you'll use a different formula for the test statistic in this case. So this will use what's known as McNamer's test, and this can be used to compare two proportions with matched pair data. In other words, if you have dependent samples. So as far as testing a hypothesis regarding the difference of two population proportions when you have dependent samples, what you want to basically do is arrange the data in a treatment. So this is the number of successes for treatment A, this is the number of successes again for treatment B, the number of failures for treatment B, and then the number of failures for treatment B, but successes for A, etc. So arrange the data in this table, and then we'll use these indices here. So then note that this is F11, F12, F21, F22. And so again, there are a couple things you have to verify to make sure that you can use this test, right? So the samples are dependent, right? And the total number of observations where the outcomes differ must be greater than or equal to 10. So again, so the steps again, which are again basically listed in section 11.1 on the bottom of page 536 and the top of page 537, are the step one again is to determine, basically the null and alternative hypothesis, right? In this case, you'll basically only have one, right? Either they'll be the same or they won't be the same. And then again, you'll have hopefully the level of significance alpha will be given to you. If not, you can assume it's 5%. And then the test statistic, in this case, the formula for the test statistic is a little bit different. This refers back to that table we were talking about. Again, you don't need to worry about where this formula is coming from, but just how to use it. So as an example, and then either again you use the classical approach or the p-value approach. And then don't forget to state the conclusion. So as an example, so let's say that a survey asked two questions of 1,483 people. Do you believe that the authorities should have the right to tap people's telephone conversations, or do you believe that the authorities should have the right to detain people for as long as they want without putting them on trial? So the thing that makes this dependent is you're asking the same people the same two questions, right? So you would ask one person the first question, and then you would ask the same person the second question of all the 1,483. So it's clearly dependent. So again, set your information up in this table, and then calculate the proportion for each situation. And then, so this will be your hypothesis, right, or the proportion of people that believe in T equal to the proportion of people that believe in D. So plug those numbers into your test statistic, and again, you can either use the classical approach, or again, you can use the p-value approach. In this case, right, you'll get a p-value about 0.5754. So in this case, the p-value is quite a bit larger than the alpha level, which is 0.05. So in either case, using the p-value approach or the classical approach, you would fail to reject the null hypothesis. And then again, don't forget to write your conclusion in words, right, so that other people that maybe aren't as familiar with the terms null hypothesis and alternative hypothesis can understand what you're talking about. So you would basically say there's sufficient or there's insufficient evidence to conclude that there is a difference in the proportion of adult Americans who believe it's okay to phone tap versus detaining people for as long as they want without putting them on trial in the event that the government believed a terrorist plot was about to happen. So, so again, that's the conclusion. So objective 5 then would be to determine the sample size necessary for estimating the difference between two population proportions with a specified margin of error. I don't know if I'm going to have you do this on the exam or not. The formula isn't really all that hard. But there will be a couple of homework problems where you'll have to do this. So I just wanted to talk about this. So sorry, this slide is kind of messy. This should be p hat. It shouldn't have the diaresis or umlaut or double dots up there. This should be p hat with an arrow above it. So the sample size that's required to obtain a you know, like a 95% confidence interval, etc., where alpha would be, in this case, 5%, is given by the following equations here. So it's n equals n1, which is equals n2, so you'll have to have the same sample size for both situations, is equal to p hat 1 times, so this is the probability of success, times the probability of failure for sample number 1, probability of success times the probability of failure for sample number 2. Again, this should be p hat with a 2 on it there. And again, because you're kind of using a confidence interval in this case, you'd want to take alpha divided by 2, look up the z value for that, and then your divide by your margin of error squared. So now in a lot of cases you may not be able to obtain a prior estimate of P1 and P2. Those may not be available. So if a prior estimate isn't available, this formula sort of simplifies. This part you can basically replace by 0.05 because that will sort of give you the maximum value. So if you use this formula, your sample size might be larger than you need, but it should be, you know, more than enough. Whereas this will get you a little bit closer to the minimum number of sample size you need to determine the margin of error. So it all kind of depends on the problem. And then just make sure you round up to the next integer, right? Because we're talking about, you know, you can't have a sample of 3.5 people, right? Because the half a person wouldn't count, right? You just round that up to 4. So as an example, let's say that a doctor wants to estimate the difference in the proportion of 15 to 19-year-old mothers that receive prenatal care and the proportion of 30 to 34-year-old mothers that receive prenatal care. And the sample size should be obtained if, or the question is, what sample size should the physician use if she wants to be within 2 percentage points with a 95% confidence interval, assuming that she uses the results of the National Vital Statistics Report, in which 98% of 15 to 19-year-old mothers receive prenatal care, and 99.2% of 30 to 34-year-old mothers receive prenatal care. And she does not use any prior estimates. So since she's not using prior estimates in this case, she'd want to use this formula, not the other one. So in the first case, right, we don't have, so this is sort of a two-part problem, right? So the first part, she wants to use prior estimates, and in this case she isn't using prior estimates. So in this case, using prior estimates, we take the 0.98 and then the 0.992 from the previous sample, right? So the 0.98 is coming from that, and the 0.922 is coming from that, plugging into the formula. And again, remember there's a 2% margin of error, right? So the 2% margin of error there. So you get about 264.5. So that means the doctor would have to sample at least 265 randomly selected 15 to 19-year-old mothers and 265 randomly selected 30 to 34-year-old mothers, right? So the doctor could get more than that, and then the margin of error could even be smaller. But again, you know, cost might be a consideration. So maybe you really do need the minimum number you would need to get that to be within the error estimate there. And again, if there weren't any prior estimates in this case, then you would use that formula that doesn't involve P1 and P2, which would be this. And so you can see that the sample size is quite a bit larger. I mean, it's obviously large enough because the minimum sample size would be 265. So if cost is a consideration, you know, you might want to somehow try to obtain prior estimates if you can. But if cost is not really a factor, right, this would obviously be far more than enough that you would need. So, so again, remember this formula without the prior estimates will usually give you more than you need for your sample. Okay, so that pretty much wraps up section 11.1. So remember that, you know, the main difference in 11.1 is you have to be careful as to whether your sample is independent or dependent, right? That will depend on the test statistic you use, and hopefully it should be clear from the problem whether you have an independent sample or a dependent sample, but if it's not, let me know. But remember, the procedure for the independent sample is on the bottom of page 531 and goes to the top of page 532, and then the procedure and the test statistic, which is pretty similar, is in the dependent case is on the bottom of page 536 and goes to the top of page 537. Right. The only difference there, I guess you might have different hypotheses you'd have to check, but you're still doing a normal curve in both cases, right? It's still a z statistic, but the formula for the statistic might be a little bit different. Okay, so and remember that 11.1 was about inference about two population proportions. So what we'll look at in section 11.2 is inference about two means. And in this case, we will break this up into two sections. So section 11.2 deals with dependent samples, and section 11.3 is inference about two means where you have independent samples. So rather covering the dependent case and the independent case in one section like we did in 11.2 or 11.1, we're going to split the inference about two means into two separate sections. 11.2 we'll talk about dependent samples, and 11.3 we'll talk about independent samples. So, all right, hope that helps. If you guys have problems, let me know.